Good evening, everyone. So today's session will discuss about the product spaces. Okay, so far we have seen measure spaces. Now we'll define measure. So suppose you have two measure spaces. So let's say mu, y, t, lambda. So these are sigma algebras, and these are the measures mu and lambda. Okay. So now the question is, what will be the sigma algebra, natural sigma algebra on this x cross y? So this is again a space. So let's say this is x tilde. So this is my new space. Now the question is, this is called product space. So now the question is, what will be the sigma algebra, natural sigma algebra, which should come from this s and t? Okay, and what will be the measure defined on that sigma algebra? Okay, so the question is, what is the sigma algebra, product sigma algebra? Okay, and then what is this product measure? Okay, so these are the two question, the first two question that we'll see. And then after this, what we'll see is that suppose you have now this measure space x cross y, so obviously we'll have some integration corresponding to this measure space and corresponding to the measure what we define here. Okay, so this will be function of two variable x and y. So what will be this integral? Okay, so how to evaluate this integral? So we know some basic stuff that, okay, so using the known measure, can we give meaning to the integration of this thing? Okay, so for example, if you have, let's say you have function of x and y, and suppose they're defined in r cross r. Okay, so it is defined on the whole real line, and then so here you had Lebesgue measure, so m1, and here also Lebesgue measure. Okay, so now the question is, so if whatever measure we define, okay, how to evaluate this integral? That is the first question. Okay, and that will be answered by Fubini-Tonelli theorem. And in fact, you will see that this can be written as double integral. This is called iterated integral under some conditions. So let's say this is dx. Okay, so d m1x and then d m1y. Okay, so the Lebesgue measure corresponding to the first variable and the Lebesgue measure corresponding to the second variable. So it will be equal to this, and this will be equal to, in fact, you can change m1y first integrate with respect to y and then with respect to x. Okay, so this will be possible, okay, under some certain condition on this f. Okay, and that will be dealt by this Fubini-Tonelli theorem, Fubini theorem just. Okay, so it has three parts. So one of them is called Tonelli theorem, but okay, so in the book it was only Fubini theorem, the name was there, so that's why I will be using Fubini theorem. So this is the whole outline of today's lecture, and after this I'll show some example corresponding to this Fubini theorem. Okay, so I mean example and then some few exercises based on this. Okay, so in this whole lecture the most important thing is this one, and for developing the theory we need to understand these things. Okay, so that's the whole thing what we'll be discussing in this lecture. So starting this with, so you have this given measure spaces, what I have just said, that our goal would be to define some measure space on this xy. Okay, and so why we want to do that? Because we want to understand the integral of this sort. Okay, so to find the integral of a function which is defined in terms of two variables and not just one variable. Okay. Okay, so okay, that's it. So now let's see. So suppose you have this measurable space xs and yt. Okay, so we define this measurable rectangle as a cross b. Okay, where this a is in s and b is in t. Okay, so I mean it's just that, I mean you just take any element from the sigma algebra s and take any element from the sigma algebra t, do the cross product. A cross product basically means this set is a comma b, where a belong to a and b belong to b. Okay, so this is just this ordered paired set. Okay, so this is your a cross b. So such set are called measurable rectangle. Okay, and then we define elementary set as finite disjoint union of such rectangles. Okay, so if you, so corresponding to this one, if you recall the first session or maybe the second one, so to give meaning of this Lebesgue measure, we started off with some set of this sort, right? A comma B, where A, B belong to R. Okay, and then from here we constructed a ring. Okay, so we constructed a ring where we took finite union of such rings, such elements. So AI comma BI, I equal to 1 to N, right? AI BI belong to R. And then we said that we have a sigma algebra generated by this ring, and that sigma algebra, we define sigma ring in fact. So for that sigma ring we define this measure and all those things. So we started our journey of Lebesgue measure from this set. Okay, and then we proceeded in this manner. In a similar fashion, we are starting with this measurable rectangle which is analogous to this one. Okay, and then we consider this finite disjoint union of measurable rectangle which is nothing but analog to this R, and then we define this product sigma algebra which is the sigma algebra generated by these elementary sets. Okay, so suppose I name this collection as E. Okay, so E is nothing but uh, finite union of AI cross BI. Okay, I equal to 1 to N, where AI belong to S, BI belong to T. Okay, and then we say this product sigma algebra which I denote by S cross T. So this S cross T will be nothing but sigma algebra generated by this E. Okay, so that's it. I mean, that's the whole thing. So this is my sigma algebra. Okay, and it is somewhere related to the sigma algebra of X cross Y, X and Y. So it is related to this sigma algebra, right? S and T. So using these two sigma algebra, we are defining a sigma algebra, product sigma algebra S cross T. Okay, so this is a natural way to define a new sigma algebra on the product space. Okay, so once we define this sigma algebra, our next goal would be to define measure on this sigma algebra, right? Okay, so before going to that, let's see what are subsections of subsets of the product space. Okay, so suppose you have E in X cross Y, then this is EX is nothing but all Y in Y such that XY belong to E. Okay, so let me for example, suppose suppose your X and Y are real number. Okay, and then you, so maybe I can draw it here. So this, so let's say this is your X axis and this is your Y axis. Okay, so this is this X is R and this Y is R. Okay, so okay. Now suppose you have some subset E. So to start with, let's say let's take the simple rectangle. Okay, so let's say you have this E. Now what is my EX and EY? That is the question. So suppose EX is how EX is defined. So you fix some X. Okay, so let's say this is your X. Okay, or X naught if you want. So it is saying that collection of all Y in Y such that XY belong to E. So now when you fix this X, okay, when you fix this X, this is the line, right? So this line is nothing but X cross Y, which is X comma Y, where Y belong to capital Y. Right, so this is your this line. Now they are saying you don't have to consider all the points Y, you have to consider points in Y such that X comma Y belong to E, and that would be nothing but this thing, right? So the points over here are X comma Y, where Y belong to, I mean these are Y belonging to Y such that X comma Y belong to E, right? So this line is the set EX. Okay, so similarly you can define this EY. This will be your EY, so E subscript Y. Okay, so these are the sections of the set E. So I hope you understand these things, right? So what is EX and EY? Did you get this picture?
Yes, sir.
Okay. So this proposition says that suppose you have E is in your sigma algebra S cross T, then this section Ex will be in T and the section Ey will be in the sigma algebra S. Okay, so if you notice, this Ex is subset of Y and this Ey is subset of X, right? In fact, this Ex will be belonging to the sigma algebra corresponding to Y, right? So if you recall, this X, the sigma algebra associated to X was S and associated to Y was T. So that's why corresponding to this Y, this Ex belong to T and this Ey belong to S. Okay, so this is a result for this subsections or the sections of this subset. Okay. Okay, so now let's
Uh,
go to this. Yeah, do you have any question?
yes, sir. Sir, if E is an elementary set, then how we can define the section?
In the same way, right? I mean, I have defined it for anything. So I took just an example to show you pictorially. So if you don't have this rectangle, okay, so let me draw it somewhere else. If I mean any set you take, so suppose this is your set E, okay, which is in the sigma algebra, then Ex would be nothing but this line. I mean, this line will be called Ex, right? This will be Ex and this will be Ey corresponding to this Y. Now if you choose other Y, this one, so let's say this is Y2, so this would be Ey2 and this one will be Ey2, right? Did you get it?
Yes, sir.
Okay. So now let's move to this monotone class. So monotone class is nothing but it is a class of subsets of X, okay, such that if you take any collection of subsets, okay, if you take its countable union or countable intersection, that will be in the set M. Okay, so M you choose, this is a subset of power set of X, okay, and this is called monotone if any family or countable family you choose in this M. So if ei I equal to 1 to infinity belong to the same, or right, so all ei belong to M, then this would imply that union of ei, okay, so the first thing is that if ei is increasing, so if ei is increasing, that is the main thing. So if they are increasing, then that would imply that union of ei belong to M, and even if they are decreasing, okay, so and same is true for decreasing also. So if they are decreasing, then the intersection would belong to M. Okay. So this is what it means by closed under countable intersection. Okay. Okay. Now this monotone class generated by a set is nothing but smallest monotone class which contains that set. In a similar way, in a similar way to how we define the sigma algebra generated by some set S. Right. So sigma algebra is generated by some set S will be the smallest sigma algebra which contains that set S. In the same way, we can define monotone class generated by a set. Okay. Let's state few properties of that. So suppose you have a monotone class. Okay. Now if you define this another collection, okay, so this U corresponding to some given P, so you choose P initially and then you define this collection which contains all subsets of X such that its union with P and its difference with P belong to M. Okay, so you have M is given to you, which is a monotone class. P is given to you, and then you consider a set of Q, I mean collection of sets of X such that the union with P and difference with P will belong to M. Okay, and that collection you called as U. So if M is monotone, then U is also a monotone class. Okay, so this is what it says. And if R is a sigma algebra of subsets of X, then the monotone class generated by the sigma algebra will be nothing but the sigma algebra generated by that set R. Okay, so suppose you have R, which is an algebra, then you have the sigma algebra generated by this and the monotone class generated by this, so they will actually coincide if R is algebra. Okay, okay. So this product sigma algebra, this S cross T, okay, is nothing but, this is by definition that it is a sigma algebra generated by elementary set, and you can you actually prove that this is a monotone class generated by elementary set. Okay, so that's just a remark for now. So the way we define sections of a set, you can even define section of a function. Okay, and this will be very much important in understanding the iterated integral. Okay, so suppose you have this measurable space xs and yt. Okay, and consider a function f which is defined from x cross y to r. This fx and fy is defined in this way, that suppose you fix x, okay, x is fixed, then you define fx, so this will be a function from y to r. So this is a function of one variable such that fx at y, okay, points of y will be fxy. Similarly, you can define fy from x to r such that fy of x will be nothing but fy x comma y. Okay, so these are called sections of function. Okay, and so for these results, so you saw earlier that if e's belong to s cross t, then ex belong to s, ey belong to t. In a similar way, if your function f is s cross t measurable, then your fx is a function from y, right? So fx will be t measurable and fy will be s measurable. Okay, fx is a function from y to r bar r. Okay, so fx is t measurable, fy, which is a function from x to r, will be s measurable. Okay, okay, so let's see few example. Okay, so how to deal with s cross t measurable function. So suppose you have this function f from x to r and g from y to r, and they are s measurable, so this is s measurable and this is t measurable. Okay, then if you define your capital fxy as fx, so this is constant with respect to y. So whatever y you choose, it doesn't matter, so it will depend only on x. So this function will obviously be measurable in s cross t. Okay, so this so you can check this one. Okay, so this is s cross t measurable, reason being that f is s measurable. So using the fact that f is s measurable, you can conclude that fxy is s cross t measurable. In a similar way, you can prove this is s cross t measurable. Okay, and the moment you say that both the functions are s cross t measurable, then their product is also s cross t measurable. So this fx into gy, so define this as phi xy, this is s cross t measurable. Okay, so what the overall result is, that if you have f from x to r which is s measurable, and if you have g from y to r which is t measurable, okay, then the function fx into gy is s cross t measurable. Okay, so that's the whole conclusion from this example. Okay. Okay, so now the times come to define the measure, product measure. Okay, so now you have this x cross y, the set. From here you define this s cross t, the sigma algebra. Now the point is to, so this, the pair x cross y comma s cross t, this is measurable space. Now if I put a measure on this, that will become a measure space. Okay, so the question is, what will be the natural measure here to make it a measure space? Okay, so now the goal is to find the measure. Okay, and this is how we define the measure. So what we do, so choose some q in this product sigma algebra. Okay, then the product measure of this q will be nothing but lambda of qx. Okay, so first you recall that qx is the x section. Okay, so let me draw that figure again for your reference. So suppose this is your q, so we are talking in r2, okay, for example, or any x cross y. So suppose this is your x, this is your y, so this is your qx, right? So we said that qx will be t measurable, right? So this qx is t measurable, so this lambda of qx makes sense, right? Okay, so is this fine?
Sir, can you please repeat it?
So what I'm saying, so you choose some q. Okay, so this is your q, which is subset of x cross y, right? This is there. Now in the in the first two slides I mentioned that if you take x section, this is the x section, right, corresponding to this x. So suppose this is the x what you fixed, then this is your qx, right? Then I said there that qx, which is subset of y, is t measurable, right? So this qx will belong to qx will belong to this t, right, this t. Now the moment I say it belongs to t, then this would imply that lambda of qx is meaningful, right? I mean the measure space. So this lambda is defined on t, so lambda of qx is meaningful, right? Yeah.
Yes, sir.
So that's what I'm saying, that this lambda of qx is meaningful, and this is a non-negative quantity because this is a measure. So lambda of qx is always non-negative. So we can define integration. So this will be a function of x, right? So if you change x, your qx is changing, right? So the moment you change x, the qx are changing. So the measure of qx is also changing. So it's a function of x, right? As you are changing x, qx is changing, and so the measure of qx is also changing. So for example, this seems to be the having the largest size, right? So this measure is, let's say, 5, then maybe this measure is 1 measure of this qx, right? So as you are changing x, qx is changing, right? And qx is changing, so the measure of qx is also changing. So this lambda qx is a function of x. So let's say this is fx. Okay, now fx is non-negative, right? So this fx is non-negative, so this integral makes sense for fx, right? Yeah.
Sir, sir, we define the x section of function or x section of a set Q.
No, we define
Yes,
both the
sir.
things. So initially we defined that if you have a set, you can define x section of that set and y section of that set, right? So I'm talking about that one at this point. I'm not talking about the section of functions. So I'm talking about section of a set. Okay, so this is your q, and these black lines are your qx. So this lambda of qx will change as x will change. So this is a function of x. So since this fx is non-negative, then all non-negative function we can define integration, right? So this is what we do. So we define the integration over whole x, okay, and with respect to the measure mu, right? Because x is given with measure mu.
Okay, sir. Sir, lambda of Qx now it is a function. It depends on the points of y.
No. See, how should, so what is qx? Qx is y belonging to y such that x comma y belong to q, right? This is the definition. This is a subset of y. So lambda of qx is the measure of this set. Okay. Now suppose I change my x as in this figure. So suppose this was my x. Now I change my x to this one. So this set will change, right?
Yes, sir.
So this measure will change, this lambda of qx. I mean, you're just measuring that length of that set or size of that set, right? So this will change as you are changing x, right? So that is a function of x, that as you are changing your x, this values are changing. The measure of that set is, the set is itself is changing. So qx is changing, right? This changes with respect to x. So the measure will also change. So this is a function of x, and so since this function is non-negative, so we can integrate that over x.
Okay, sir.
Okay. In a similar way, I mean, here instead of taking this x section, you can do the same thing with y section. Okay. So now you fix a y. So this will be your qy. Okay. Now you change your y, this qy will be changing. Okay. And this measure will be, this qy is a subset of x. So this mu measure will be defined. Now this is again a function of y. Okay. So now as you change y, this function will change, and this is non-negative, so you can integrate. Okay. Now this quantity is called the product measure of q. Okay. So this is how we define. Okay. Now if you recall, so for defining the integral, okay, how we started with, so we started was, first we defined that integration of simple function. Okay, so at first the function f was measurable. Okay, then we said if f is simple, how we define the integration. Then we defined f for non-negative, right? So for non-negative we defined using the approximation of non-negative function by simple functions. Okay, so we know that any non-negative function we can make sense of integration if it is measurable. Okay, so for making sense of this integration, we have to make sure that these function, which is fy, or let's say this is gy, we have to make sure that this fx and gy are measurable. They are non-negative, so the only thing what we need to make sure is that they are measurable. Okay, and in fact they are measurable. Okay, so there is one result, and this should be equal as well. Okay, if they are equal, then only we can define this as a common quantity. If this is different, if this is different, then how can we define this mu cross lambda, right? So we have to make sure three things: that this function, that this map is measurable, this map is measurable, and they two, both of them are equal. Okay, and that is in fact true. Okay, and this is the precise theorem, okay, which says that. Okay, so I'm just leaving this statement, so this is true. Okay. Okay, so now uh, let's see some example of this product measure space. So suppose you have this x and y to be the real line. Okay, and you define this E to be this set. So this is nothing but, so suppose this is just the x axis, right? So this is x axis. Now you can write this x axis as this union. So this is nothing but, so this is r, so this is 0, so you are writing 0 comma 1, 1 comma 2, 2 comma 3, this minus 1 comma 0. So in this way. Okay, and just because of this 0, you are writing this cross product. Okay, so this is how you can write this x axis as disjoint union of this half open half closed set. Okay, then the measure of this E. Okay, so E is now a subset of x cross r in some sense. Okay, so I mean, so this was your, this is your x, this is your y. Okay, now I am asking that the measure of this thing, Okay, what will be that in product measure? Okay, so one thing is that you can look, this x is just a real line, so you know that m1 of x, I mean the Lebesgue measure of this x is infinity, right? But I am not asking about this m1, I am asking about this measure of this thing. So as a subset of R2, so this is a subset of R cross R. So what will be the product measure of this E? Okay, so let's go through the definition. So m1 cross m1 of E will be integration over x, right, and m1 of ex. Okay, so what will be the ex? Ex will be just one point, right? So ex, you just check that ex will be singleton x, right? So there will be this, these are all ex, right? So m1 of ex will be what? It will be 0, right? Lebesgue measure of a singleton is 0, so this will be 0, and so the integration will also be 0, right? Okay, I mean I should have not just singleton x but as a ordered paired. Okay, so x comma 0. Is this fine?
Yes.
So this
Sir,
m1, yeah.
sir, then we have also to define the y section of E.
Yeah, if you define y section also, then if you go for the y section, so how will you define? If you define, so you will integrate over y, okay, and then you will look for m1 of ey, right? And what will be ey? So if you look ey will be, I mean this will, so if you go through the definition, ey will be phi, right? So if you write definition somewhere, so let me write it here. So ey is the collection x of x such that x comma y belong to E, right? And what is your E? So xy belong to E if y is 0. Okay, so ey will be R if y is 0, else ey will be phi if y is non-zero, right? Did you understand this one? And this is just
Yes,
from the
sir.
yeah. Okay, so now if you want to integrate this m1 of ey, okay, so m1 of ey will be okay, so m1 of ey is almost 0, right? At just one point it is taking the value infinity. So you see that e of 0, e of y is almost 0, right? Ey is 0 almost everywhere. Can I say this? I mean not 0, but I mean m1 of ey, right? So if you consider this as a function of y, this measure of ey will be 0 because ey is phi. Ey is taking the value whole real line if y is 0, which is just one point. So m1 of ey is 0 almost everywhere, and so this integration is 0, right? The reason being this. Okay, so whatever way you go through, you will get that this integration is 0. That means this product measure of E is 0. Okay. Okay, so now let me tell you the difference. So you, let's say you are in R2, okay. So in R2 you have the Lebesgue measure. So in R2 you have this Lebesgue measure M2, right? Just a second. So yeah, so what I was saying that in R2 you have this Lebesgue measure M2, and now I am defining one more measure as a product measure, right? So on R2 you have this, and now you are having this also, M1 cross M1, right? Now the question is, will are they same or are they different? Okay, so this is the question, that what is the relation between these two things? They are the measure on the same space, right? So let's see that. So now you choose some E, okay, which is not Lebesgue measurable. Okay, then you know that this E cross 0 is not in the Lebesgue measure, not in the sigma algebra of product spaces. So this does not belong to LR cross LR, right? Just because E does not belong to LR. Now if you calculate this M1 cross M1 of E cross 0, you are getting 0, right? So from above you know that this is always going to be 0, but you know that this is not measurable, right? So that means this measure space, okay, R cross R with the product sigma algebra and with product measure is not a complete measure, because you have a measurable set, non-measurable set which is of measure 0. Okay, so it is not complete. Okay, but you know that Lebesgue measure is always complete. Okay, so now instead of this LR cross LR, if I consider this LR2 with, instead of this measure M1 cross M1, if I consider M2, so what I am saying is R cross R with Lebesgue measure R2 and with M2, this is a complete measure space, right? So this is complete, but this is not complete. So obviously these two are different. Okay, so this E cross 0, this belong to LR2. Why? Because the measure of this quantity M2, so yeah, this is written here. So this M2 of E cross 0 will be 0, right? I think this was done in the very beginning, that if you choose any subset, okay, if you have any subset of dimension less than that, so if you are in Rn, okay, and if you have subset E of Rn which is of dimension k which is less than n, then you know that the measure of this thing will be 0, the Lebesgue measure. So this Lebesgue measure of E cross 0 will be 0. Okay, so this E cross 0, since it is a complete measure space, E cross 0 will belong to LR2, okay, the Lebesgue sigma algebra, and not the product sigma algebra. Okay, so this E cross 0 does not belong to the product sigma algebra of Lebesgue measure in R, but this belong to the Lebesgue sigma algebra of R2. Okay, so these two are completely different, and in fact you can prove that this measure M2 okay, is completion of M1 cross M1. Okay, so you start with this M1 cross M1 with the sigma algebra LR cross LR, and if you start completing it, completion means what? You are putting some null set in that. Okay, and this M1 cross M1 will be equal to M2, okay, on the set LR cross LR. Okay, so they are equal on this set, you can show that. Okay, so this M2 is an extension of this M1 cross M1, I mean it's completion of M1 cross M1. Okay, okay, so did you get this point, I mean this difference?
Yes, sir.
Okay, so now let's move to this Fubini theorem. Okay, so I mean this seems to be very complicated one, but it's not that. For the use, you can just remember 2-3 things. So what are that? So suppose you have this x this xs and y t lambda, two different measure spaces. Okay, and suppose you this f is a real valued function or real extended real valued function defined on this x cross y. Okay, so it is a function of two variables. Okay, and this is s cross t measurable. So since this is s cross t measurable, this integration makes sense. Okay, now the question is that how to evaluate this integral using the iterated integration. Okay, can this integral will be equal to this type of integral? Is it true? So it will be true under certain condition. The first condition is what it talks about. So suppose this f is non-negative, that means the function is greater than equal to 0 for all points. Okay, in that case this will be always true. Okay, so these things what is written here, okay, these things are just to give meaning to this identity. Okay, so it says that this function phi x and psi y are measurable. Since they are measurable and also they are non-negative, right, because f is non-negative, so fy is non-negative, so this integral is non-negative. So since this is measurable, this integration makes sense. So this imply that this integral makes sense. Okay, and this condition imply that this integral makes sense. Okay, so overall what you can remember, that suppose you have a non-negative function, then this f on x cross y, okay, with this product measure, integration will be same as you integrate first with respect to x and then with respect to y. Here you or you integrate first with y or with x. Okay, so when you have non-negative function, you can do the iterated integration. So such integrals are called, so this integral and this integrals are called iterated integrals. Okay, and you must have seen many of the times that suppose you have this fxy in, I am just talking about this Riemann integration dx dy, suppose a to b and then c to d. Now the question is, when can you interchange this with this one? So this says that you integrate first with respect to x and then you integrate with respect to y. Now the other, will it be equal to fxy dy dx? Okay, so now the limit will change, so now c to d and then a to b. So are they equal? So this Fubini theorem will tell when they will be equal and when they will not be equal. Okay, so this will be useful. So the main point what you can remember from here is this one, this identity. So when this will be true. Okay, in a similar way, okay, let me first state this c part. So what it says, that if you have integrable function, okay, on xy, so here what did you have? You have that if the function is non-negative, then you have such identity. Here they are saying now we are going to more general setup, right? So if you have any integrable function on this measure space mu cross lambda, I mean with measure mu cross lambda, then you can again do so. Okay, then again you can do this type of thing. Okay, so what is true for non-negative function is also true for any integrable function. Okay, and then the question would be how to check integrability of this thing. Okay, now for checking integrability, you will have to use this a part. Okay, so I have few exercises. At last I have put some exercises, so maybe, I mean, from those examples it will be much more clear, okay, how to use these things. Okay, so for now you just remember that if you have non-negative function, you can do this thing. If you have any integrable function, then also you can do this thing. Okay, and what this says, that suppose this mod of fx, okay, so the x section of this mod f, okay, so here you are considering the, so suppose this is your g, then g is non-negative. Okay, so that's all they are making sure. So if mod of f, the x section or the y section, okay, any one of them, if you can make sure that any one of them, this thing is integrable, okay, then again you have this equality. So suppose you can prove that, you prove that, okay, this 5 star is integrable with respect to x. So this is just a function of x, right, because you have integrated over y. So this is a function of x, so let's say f tilde x. Now if this f tilde x is integrable with respect to x, then this mod f will be equal to, so this is nothing but x, y and then mod f x d lambda d mu, and this is nothing but mod f y x y d mu d lambda. Okay, so again similar sort of identity is true. Okay, so if any one of them is integrable. Okay, so this was all about this Fubini theorem. Now let us see some example or application to this Fubini theorem. Okay, in fact, if you look at these two results, this has already been proved using, so this was proved using monotone convergence theorem and this was proved using DCT. Okay, so what it says, that if you have some function of two variable defined over natural number. So this is n cross n, okay, with pn cross pn, okay, and then you have the product measure, which is counting measure, okay. So product of counting measure. So on this space, if you define your fmn as amn, then using the Fubini theorem, you can prove that this will be, I mean, either you sum, okay, so I think there is a typo. So here it is basically this, I think there you can find. So this you sum over n first and then over m, or you sum over m first and then over n, okay. So they are interchangeable, okay. So this is all, this is the application of a. So using this a part, okay, so it's just the a part, okay. So you just have to put this function and you have to consider that the measure what we are considering is the counting measure. So in counting measure, the integration changes to summation, okay. So that's all. So this is nothing but a of Fubini theorem, okay. So this is by a, and this one is by c part. What it says that if you have this function amn and you know that the double summation, okay, everywhere it's the same, so either n or m, anything you take, and if the double summation of this modulus is finite, then again you can interchange them, okay. So this is n, this is n, okay. So this is an application of this Fubini's theorem in this counting measure setup, okay. Now let's come to this one. So again you have this x and y are natural number, okay. Okay, I think one thing I left to mention it, that you have to note down that this, the measure space what we are considering are sigma finite measure space, okay. So this is very important. I'll give you an example. When the measure space is not sigma finite, then this will not hold true, okay. In fact, this is the no, this is not that example, but okay. So what it says that suppose you have x and y to be the natural number and you define this function fmn and this, then now if you sum this, okay, so here it will be n first, okay, n. So now if you sum this, or am I wrong? Let me check. No, it's fine, I guess, okay, yeah. So so when we consider n first, okay, let's try to see. So what is the definition of amn? That it will take the value 1 when n is 1. So a m comma 1 is 1 and a m comma m plus 1 is 1 minus 1. Rest are 0, right? So now if you see this summation a m comma n, and if you are varying this m, okay, so m will be first, don't know, just a second, yeah, okay. So you are considering this summation first, okay. So when n is 1, this will be 1, okay. So this will be non-zero, so that's why am1. The next step, am2 will be 0, am3 will be 0. So I mean, so once this m is fixed, okay, so here it will be m. So once you are fixing this m, only two quantities will be non-zero, a m comma 1 and a m comma m plus 1, okay. So that's the only possibility for if m is fixed. Now you just vary over m, then you get that this is nothing but am comma 1 is 1 and you know this is minus 1, so this whole quantity is 0. Now you sum 0 infinite many times, you will get 0, okay. Now in a similar way, if you start with this one, okay, just a second, yeah, okay. So now you see the other way around. So now you sum over m first and then over n, okay. So if you consider this n, let's start with n equal to 1. So if n is equal to 1, this will be the summation, right, for n equal to 1. For n equal to 2, this will be the summation. For n equal to 3, this will be the summation, and so on, right. So you are breaking this series, okay, this series, and then you are writing it in this fashion. That's it. Now you see this quantity. this one, you know that a m comma 1 is always 1, so this is an infinity, right? So this is infinite because you are summing 1, so this is 1, right? So this is infinity. Now this a m comma 2, if m is 1, then this will be minus 1, so this will be minus 1 if m is equal to 1, else 0, right? Else it will be 0. So this whole summation will be minus 1. Similarly, this will be minus 1. So if you take any partial series of this, partial sum of this series, you will get infinity, right? So partial sum of this series is equal to plus infinity. So the series is divergent and it diverges to plus infinity. So you can clearly see that order matters. So when you are summing n first, I mean the summation have n first and then m, and when the summation has m first and then n, then the values are not equal, okay? And the reason being why it is happening, because so it is not contradicting our theorem. So the theorem was saying that if you have any function f, okay, so for making them that these two things will be equal, you have to make sure that this integral, this summation, okay, this summation should be finite, right? And in fact in this case this is infinity, okay, and the reason being same, I mean, as this one, okay. Right, here order does not matter. So here you can see either you can do, so again there is a typo, so you just write n here. So this is equal to m equal to 1 to infinity, n equal to 1 to infinity, mod a mn. Can you tell me the reason? The reason is the first one, right? So if you recall this, so this is by a of Fubini theorem. Why? Because these are non-negative. So for non-negative function you can always interchange the integrals, and in this case you can interchange the summation, okay. So you can clearly see that this will be infinity, right? If you consider here also, then this mod, this will be mod, this will be mod, so it will be 2. Now you're summing 2 infinite many times, so it will become infinity, okay. So the main reason for these two not equal, not being equal, is this one, that the summation of modulus is infinity, okay. Okay, so let's go to this third example, which shows that the sigma finiteness of the measure was very necessary for the Fubini theorem, okay. So now you just take this example. So x and y are your this interval 0 1, and then you are considering the Lebesgue measure, but sorry, Lebesgue sigma algebra, but the measure, one of the measure is Lebesgue measure, the other measure is the counting measure, okay. So that's the difference. So you know that this counting measure uh, is not sigma finite, right? Because if you partition 0 1 as countable union of any sets ai, then you know that the counting measure of ai will be either 0 or infinity, right? So this lambda is not sigma finite, okay. Okay, so this is not a sigma finite measure. So now we'll see that how these integrals are different. So let's first see this one. So let's start with this quantity. So this one, if you see, okay, so this I can rewrite as, so let me write, so first let us see what this d is, then I think it would be more clear. So this is your d, so it's 0 1 cross 0 1, so let me make it in this way. So this is your 1, this is your 1, and d is this diagonal, okay. So this is your d, okay, and the function f is the characteristic function on d, okay. So it is the characteristic function on this diagonal, okay. So what does this function say? This will be 1 if x belong to d, I mean if x comma y belong to d. So you know what the characteristic function is. This is if x comma y belong to d, and 0 if x comma y does not belong to d. So this is the definition, okay. Now let us try to see what this integral would be, okay. So this integral is nothing but, I can write this is y, okay, this is x, and this is nothing but f y of x, right? So d mu x d lambda y, okay. So this f y x, okay. Now let us see what will be f y of x. So f y of x will be f x comma y, right? So this is by the definition, this is the definition. Now f x comma y, so the moment you fix y, okay, so when y is fixed, then it will be taking value 1 if x is equal to y, right? This is what this definition says, that if x y belong to D means that if x is equal to y, and if, in other words, this is what it means if x is not equal to y, right? So when you fix this y, so when you fix this y, okay, then this fyx, which is a function from x to r, okay, that is taking value 1 if x is equal to y, okay. So that means this quantity will be 1 when x is equal to y. So that's why I can write this as y, and this is when x is equal to y, 1 d mu of x d lambda of y, okay. Now what is the integration of this quantity? Okay. So this is first let us integrate with respect to x, then what will be this quantity? This will tell you that the Lebesgue measure of the set x equal to y, which is 0, right? Because it's just a single point, right? So this integral is nothing but mu of x, I mean y is fixed, so it's like mu of y, okay, and this is 0 right? So this is 0, so the whole integral is 0, okay. Now let us see what is fy. So now let's come to this one, let's come to this quantity. So this is nothing but, so this is x and y. Now you are fixing x, okay, x you are fixing, and y d lambda y, and then d mu x, okay. So you are integrating first with respect to y. So let us see what is fxy, okay. So if you, let me just shift it a bit, yeah. So if you go for fxy, so here x is fixed, so this is fx comma y, this is by definition, this will be 1 if y is equal to x, right? So this will be equal to x, and this will be so y equal to x, and this will be 1 d lambda of y d mu of x, right? This is what this integral would be. Now this is integration over x, and this quantity is nothing but the measure of, so this is lambda of this x equal to y, so this is lambda of x okay, and then you are integrating with respect to x, and you know this lambda of any singleton set is 1, I mean this is a counting measure, so this is 1, so this is x 1 d mu of x, and this is nothing but mu of x. And what is mu of x? So x was your 0 1, right? So the Lebesgue measure of 0 1 is 1, so that's why this integral is 1. So is this clear?
Yes, sir.
Yeah, okay. Okay, then let's start few problems based on these things. Okay, so let's start with this problem. So it says that you have been given two functions, okay. So you starting with this 0 1 cross 0 1, okay, and then you have to say, okay, I think here something is wrong here, I think. So this is again a typo, I guess. So here it's asking about d m1 cross m1, okay, yeah. So you have to investigate that this integral of f with respect to the product measure, and what are those integrals, that whether they will exist or not, and if they exist will they be equal or not, okay. So the question is that you have to prove that these quantities exist or not, and if they exist, will they be equal? Okay, so that is the question. Okay, so let's start with this B problem first. Okay, so this B problem, okay, so this you see this f(x, y) is always greater than equal to 0, right? Because x and y are in 0 1 interval, so this xy is always less than or equal to 1. So this quantity is always greater than equal to 0. So by by a part, okay, by a part of Tonelli, sorry, Fubini's theorem, you know that all this integral, this f e d m1 cross m1 will be equal to this double iterated integral fxy. Okay, so if you can write in this way, so d, so what are the measures? So m1 x d m1 y, so this is over 0 1 and 0 1. Okay, and this will be same as, so this is just from Tonelli. Okay, and if you want to calculate the integral, you have to do a bit work to calculate this integral. Okay, so this is x, this is y. Okay, so this is all about this B part, but for the first one, you can clearly see that this is not at all a non-negative function. So depending on the value of x and y, this function may be positive or may be negative, right? So we cannot use this a statement of Fubini. Okay, so let's see how to deal with that. Okay, so so to start the journey, let us first see how these integrals are there. I mean, how these can we calculate this integral? I mean, can we get some finite value of this integral? So let us check that one. Okay, so let's start with this first integrating with respect to x. Okay, so this is, you want to know 0 1 0 1 dx dy. Okay, so let's start with the 0 1 fx comma y dx. I want to integrate this with respect to x. So what is your fxy? This is x square minus y square. This is 0 to 1 x square minus y square, x square plus y square, and then you dx, right? So this is what you have. Now you just do change of variable, so you can substitute x by y tan theta. Oh, sorry, y tan theta. Now if you do this substitution, so when x is 0, your theta will be 0, right? So and when and when x is non-zero, when x is 1, then your theta will be tan inverse 1 by y, right? So this will be the limit, and then you have this y square 1 minus, sorry, tan square minus 1, and here you have, okay, I think there is a square, right? So here you will have y4 and then tan square theta plus 1, right? And then d theta. So this 1 by y square will come out. Okay, sorry, d theta not. So x will be y sec square theta and then d theta, right? So this will be the d theta. So now here you can write 0 tan inverse 1 by y. So this will be 1 by y square, and then here you have this tan square theta minus, so this tan square theta plus 1 would be, so again here it should be square. So this is tan square theta minus 1 as it is, but in the denominator you have the sec square theta and then square, right? So this is sec square theta, and then 1y will cancel d theta. Now this sec square theta will cancel this one, so what you have is 0 tan inverse 1 by y, 1 by y. Okay, and then you have so this, if I split this one, tan square by sec square would be sine square, and 1 by sec square would be cos square theta d theta. Now again, if you do 0 to tan inverse 1 by y, okay, so this sine square minus cos square is nothing but cos 2 theta, and then this is d theta. Now again 0 to tan inverse 1 by y. This is, so this 1 by y I can take outside, right? So it's better to write outside. This is 1 by y, and this cos 2 theta, if you integrate, so you'll get sine 2 theta, right? So you get sine 2 theta and 0 to tan inverse 1 by y, right? So now if you break that, so you'll get sine okay, then okay, so sine I somehow I'll have to convert into tan theta, right? So okay, so first I think, okay, so first let's break this sine theta. Okay, so sine 2 theta, so you know this is 2 uh, just a second, yeah, okay, so this is 2 sine theta and then cos theta, and these are the limits 0 tan inverse 1 by y. Let's see, so this is 1 by, so this is 2 by y now. Okay, I think here it should be 2, right? So when we integrate, so this 2 will not be there, so then this will be, okay, so now I want to convert sine into tan theta. Okay, so what I do, I multiply and divide by cos theta, so I'll have tan theta, and here I'll have sec square theta, sorry, cos square theta, right? Just a second, so sine by cos will be tan, and then cos square theta, so 0 to tan inverse 1 by y. Okay, and again cos square you can write it as 1 by sec square. Okay, so you can write it as 1 by sec square theta, and now sec square theta can be written as 1 plus tan square theta. Okay, so so what you can do, instead of writing 1 by sec square, you can write 1 by 1 plus tan square theta. Why I'm doing this? Because I want to remove this tan inverse, that's the only point. So this will be 1 by y, and then you have tan of tan inverse 1 by y. Here you have 1 plus tan square of tan inverse 1 by y, right? And at 0 it will be 0 if I put, so this is the only thing what I have. Now this is 1 by y, this tan of tan inverse will be 1 by y. Here I'll have 1 plus this tan square, so this is tan of whole square, right? So you can write it as this. Now tan inverse 1 by y will be 1 by y, and then 1 by y square would be 1 by y square. See, now you just take the LCM, so y square, so you'll have y, no, here there will be no y, so it will be 1, and then 1 y will cancel, so this will be 1 plus y square, right? So this is the value of this integral of fxy with on 0 1, right? So this is all you have. Now you have to integrate with respect to y as well. So this integral, so this integral, now we integrate with respect to y. So this is 0 to 1, 1 by 1 plus y square dy. Okay, and this integration is nothing but tan inverse y 0 1, and this tan inverse 1 would be pi by 4, and this will be 0, so it's pi by 4. Okay, so this integral exists. Okay, so this integral exists now. Okay, so this is finite. Now just note one thing, so let us see this one. So what we have to check, the x square minus y square, x square plus y square whole square dy dx, right? This is what we need to make sure. The next goal would be to make sure this one. You can clearly see that this I can rewrite as 0 1, so 0 1 0 1 y square minus x square by x square or y square plus x square whole square and with minus sign dy dx, right? This I can write. Now you compare this quantity, okay? I mean, you compare the whole quantity, this one maybe. This you consider what this is saying, that x square minus y square, then you have dx dy. In the same way, y square minus x square, you have dy dx. The denominator is same. It doesn't create any problem. So the only thing is that, so in the numerator part, so you see that this quantity is same as this one, right? This is equal to this quantity. The only difference is that instead of y and x, we are writing here, I mean, the role of y and x is interchanged, okay? But that's not a problem because here the role of integration has also changed, okay? So they are just a notation. So instead of y x, you can even write z or w, okay? So that's not a problem. So the main point is that this whole integral is nothing but pi by 4, like above. So this integral is minus pi by 4. So you clearly see that these two are not equal, right? So they are two different quantities. I mean, the value is different. And so since they are not equal, so since this dx dy, since they are not equal, so this e, right? So I think e was there. Yeah, so this integration over e of this fxy, or x square minus y square by x square plus y square whole square d of m1 cross m1 will not exist, right? Because if it exists, right, then by tonally theorem you know that this and this should be equal. So all three should be equal. So by this, so this is by C part, okay? So C part of Fubini theorem. So it's a contrapositive statement, okay? That if suppose if this exists, then you would have got that these two are equal, okay? Okay, if this is fine, then, so is there any doubt in this problem?
Sir,
Yeah.
When we integrate, where we put it cos 2 theta. Yes, sir.
Right.
Yes, sir. There should be minus.
Here it should be.
Yes,
Oh,
sir.
okay. So it's cos square minus sin square is cos 2 theta, right?
Yes, sir.
Yeah, you are right.
Should be both are equal.
So here, no. Then here minus, 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 and then here also minus. So you will have minus pi by 4 plus 0. So it is minus pi by 4. And here you will have minus with this minus pi by 4. So it will be plus pi by 4, right? Right, so this is minus of the integral obtained above. So it is always, they are always going to be different. Yeah. Yeah, thanks for pointing it out, that one.
Sir, we are just putting by changing the variable.
You are talking about this one?
Yes, sir. The second integration,
this one,
dy dx. Yes, sir.
Yeah, I am
Yes,
saying that, see, yeah, you can consider it as a change of variable, but what I am saying, that this y and x are just a notation, right? You compare this integral with this one. So both are over 0, 1, 0, 1, right? Here it's x square minus y square, then you have dx dy. Here also you have y square minus x square, then dy dx. So corresponding to the y square you have dy, corresponding to x square you have dx, right? So in that sense I am saying these are the same quantity actually. You just interchange the role of x and y. So what you are saying is also the same, but I mean the problem is that you cannot do the change of variable simultaneously. I mean, I mean, y going to x and x going to y. I mean, this is quite absurd, right? So, but you understand what I'm trying to say. I mean,
Yes.
these are actually the same quantity. Okay. Okay. So if yeah, so we concluded that this integral will not exist. This integral does not exist. Okay. Now let's go to the next problem. Okay, so what this question is saying, that suppose you have a Lebesgue integrable function on 0a, okay, where a is obviously positive, and you define this gx as t inverse ft dt. Then you have to prove that g is integrable on 0a, okay, and the integration 0a gx will be equal to the integration of f over 0a. Okay, so they will be the same quantity, the integration. Okay, so let's see. Okay, so let's first check that g is integrable. Okay, now for integrability, what you have to check that 0a mod of gx dx is finite, right? So this is what it means by checking the integrability. So let's start with that. So 0a mod of gx, okay, and this is equal to 0a mod of gx is, so this is 0a t inverse of ft, right? Okay. So now I can use this inequality to get 0a. Okay, so let me write dt. This is dt and this is dx. Just a second. So this is x, right? Yeah. So this is x comma a t inverse mod ft dt dx. Okay. Okay. Now you can rewrite this as 0a, okay, 0a chi of x comma a, right? So instead of 1, so here 1 is there, so instead of 1 I'm writing chi x comma a t inverse mod of ft, okay, dt dx. Okay, now the next thing is that here you see this quantity, this is non-negative function, and this is measurable, because f is measurable, f is integrable, so it is obviously measurable. It's given to you that it's measurable, and all are non-negative. Okay, so this whole quantity is non-negative and they are measurable functions. Okay, so by a part, okay, so what you have is you can rewrite it as 0 to a, 0 to a, so you can, so let me write in this way, 0 to a chi of x comma a dx. So what I am doing, I am interchanging these two things. Okay, so this is possible by a of Fubini. Okay, so once I interchange it, you see that these two functions are independent of x, so I am putting it outside x. So t inverse mod ft and then dt, right? Okay, so this is 0 to a. Okay, now let's check what this chi of xa is. Okay, so you see this chi of x comma a, what is the definition? The definition says that this will be 1. So okay, one more thing, so this is chi x and sorry, so this is a function of t, right? So just a minute. So this is a function of t. Why? Because we are integrating with respect to t. So if I want to replace, I want to put, instead of 1 I want to put this chi function, I'll have to take it as a function of t. Okay, so this is a function of t, but x is involved here, okay, in the definition. So that's why dx will be here. I mean, we have to keep this with dx. Okay, now let us see what is chi x a of t. So this is nothing but, by definition it's 1 if this t lie between this x and a, right? But it will be 0 if 0 less than t less than x, right? So this is the definition of this characteristic function, right? Now you can rewrite this one in a different way. So here you have in terms of t. Now I want to write in terms of x. So let me rewrite this. So you can you can clearly see that this function can be thought of. So you see these two things, that x less than equal to t and x greater than t. I mean, yeah, x greater than t. So what it says, that if your point x is lying between t and 0. So just a second, that x is less than equal to t, and here it says that x is greater than t. Yeah, so I can rewrite this chi as a function. So I want to write it as a function of x, okay, and if x is less than t, then I'll get 1, okay. If x is greater than t, just a second, no, I mean, if x is less than equal to t, then we have 1, right. Then if x is greater than, what should be there, okay, just a second. Yeah, okay, so so you put 0 here. Yeah, do you have something to say?
No, sir. I am also saying 0.
Yeah, exactly, because if x is greater than this t, then it will be 0, okay. So that's why we have to consider this interval, right? Yeah. So so I just wanted to write this function as a function of x, so that I can integrate it, okay. So this is 0 to a. Instead of this chi of xa, I will write chi of 0 comma t as a function of x, and then dx. This is t inverse mod of ft dt, right? Now I can write it as 0 to a, and then this, if you see, this integral is just characteristic function, so this integration will be nothing but the measure of this thing, right? So this is, so actually if you see, this integral is nothing but 0 to t 1 dx, right? This is all it is. So it's nothing but t into, so this is t inverse mod of ft dt, and this is nothing but 0 to a mod of ft dt, and you know the function f is integrable, so this is finite. So this proves that this g is also integrable, okay. So this g is integrable over 0 1, okay. Now the next question was, what will be the integral of g, okay. So the next question is,
Sir,
yeah,
sir, 0 to ax, yes, the integral will be, no, sir, the next
oh,
one, yes,
this
sir.
one 0 to a, right?
Uh, no,
Yeah, what are you saying?
sir, the integral change, the characteristic on 0 to t, it will be equals to be 0 to t 1 dx. So how it is?
Yeah, so what is the integration of this? This just, how do you integrate this?
No, sir, sir, it will be equals to be the above integral.
So you are saying how this equality is coming?
Yes, sir.
Oh, so I mean, so this is 1 when it's in 0 t, right? And if it is greater than t, it's 0. So it's like, so suppose this is your 0, this is your a, and the function is like this 0. So suppose this is your t, so this is 1 here, and this is 0 here. So what will be the integration of 0 to a? You just have to consider 0 to t, right? So suppose you have c here, okay, and the function is this. So what will be the integration fa fx dx? Tell me. It will be a to c, the function is taking value 1 dx, plus c to a, the function is taking value 0. So this will be gone, so this will be a to c dx, right? In the same way, it's from 0 to t will only matter. Did you get it? Yeah?
Yes, sir. Sir, the point where a when x is less than 8.
When x is less than
Yes,
a.
sir.
Yeah,
When
so
t
see,
is n and
t
is
is lying between a and 0, right? So t is some point in this region, between these two, 0 to a, right? So t will be somewhere here in this, between this 0 and a, right? So t is, let's say t is here, so this is the function and this is the integral.
okay, sir.
Yeah, okay. If you want, let me keep it there itself. Okay. Yeah, so now let's proceed to the fact to find the integral of g. Okay, so you have to find g of x dx 0 to a, right? So what will be the integral? So this is 0 to a, and what was your gx? Gx was x to a t inverse ft. So this is x to a t inverse ft dt, right? This is your gx and then dx, right? So this is 0 to a x to a t inverse ft dt dx. Now you know by the above thing, so okay, so you know that this function, so so how should I write that? If this so x comma a to 0 comma a, this is t inverse ft. You have shown above, right, that this is finite, right? This is what you have shown. This is nothing but mod of gx, right? You have shown this one above. This means as t inverse ft. Okay, so let me include this characteristic function to be more, I mean, to look good. So you can write it in this fashion, right? Chi of x comma a, okay, mod of this one. So this is finite. This implies chi, here also you can write in that way. So 0 to a chi of x comma a, okay. So this chi of x comma a t inverse, so this is by above, this is finite, so this t inverse ft is integrable, right? So this means if this is integrable, then by c part, so I mean use c of Fubini, right? So you can use c of Fubini to get this 0 to a chi of x comma a t inverse ft dx dt, right? So I have changed the role of dx dt, okay. Now again, I mean, I will not repeat this, but this will be coming out to be this quantity, right? 0 to a with, instead of mod f, I'll have ft. So this will be 0 to a, right? Because if you integrate this, so this is nothing but chi of 0 comma t, right? And if you integrate, you will get t and t inverse will cancel, so you will get 0 to a f of t dt, right? This is what you get. So this is what you needed to prove, right? That the integral of g and integral of f over 0a is same, okay. Okay, so is there any doubt?
No, sir.
So you have seen how to utilize this Fubini theorem, right? And in these examples, okay? So at least in this example. Now let's see one more example where it will be used, okay. So this first part I have already answered in one of the tutorial, maybe in the 6th session, I guess I dealt with this one, okay. So the idea was very easy, so let me just repeat once. So this 0 to infinity mod sin x by x, right? So what you do, you break this integral in summation, so n equal to 1 to infinity, so 0 to infinity, do n pi to n plus 1 pi, okay, and then this mod of sin x by x. Now you know that this x can be bounded below, 1 by x, infinity n pi to n plus 1 pi mod of sin x by n plus 1 pi, right? And this sin x function, if you integrate, so this you can take out, so this is nothing but, just copy this one, and so this is the same, so only you need to integrate, so you need to integrate, so this n, this I can keep outside, right? So you have to integrate this one. So this I am taking out. Now you know this sine function, mod sine function is like this, right? And each this area is nothing but pi. So this integration is pi. This integration is pi. So what this is turning out to be, this is n equal to 0 to infinity 1 by n plus 1, and you know that this is infinite. This series diverges. So this integral is infinity, right? Right? So you know that this function is not L1 function, okay? But you have to find that this integration of fx over 0 infinity, so you have to write, so since we are dealing with this Riemann integration, so it has been written in terms of limit form. So you have to prove that this limit of this integral as b goes to infinity will be pi by 2. So the modulus is not, the integration of modulus is infinity, but if you remove the modulus, it is turning out to be finite value, okay? And I said in that session that you can prove it using complex analysis tools, but in fact you can prove it using this Fubini theorem as well, and how to use that I'll explain. Okay, so this b part, so let's see what is this 0b, so x inverse sin x, okay? You have to find the value of this quantity, right? So what you can do, let's see what is x inverse, this x inverse. So if you want to use Fubini Tonelli theorem, you know that you have to write it as a function of x comma y. So there should be two variable, okay? So you note this one thing, that 1 by x you can write it as e raised to the power minus xy from 0 to infinity. So let's integrate this. So we'll have e raised to the power minus xy upon minus x and then 0 to infinity, right? Now you put infinity, you will get 0. So this 0 minus, if you put y equal to 0, so this is with respect to, y, okay? So if you do, so y equal to 0 would give you 1, so 1 upon minus x, so you'll get 1 by x, right? So this 1 by x which is coming here, so this 1 by x I can replace by this quantity, so 0 to b 1 by x sin x dx, I can rewrite it as 0 to b and then 0 to infinity e raised to the power minus xy dy and dx, right? So so far okay, sin x and dx, okay? So if I want to write complete manner, I can rewrite it as 0 to infinity e raised to the power minus xy sin x dy dx, okay? Now the question is, can we interchange this dy and dx? So can we apply Fubini theorem? Okay, so for applying Fubini theorem, since this is a normal function, this function will take positive negative value both. So what we need to make sure, okay, so what we need to make sure to apply, so let me write it here somewhere. So for Fubini, you want to make sure that this 0b cross 0 infinity, this e minus xy sin x, okay, the product measure, so d m1 cross m1, the Lebesgue measure, is finite, right? If you can prove that this is finite, then we can use Fubini and it will be 0 infinity 0b e minus xy sin x dx dy, right? So I have interchanged this one. So we have to first make sure whether this happens or not. So let us check. So this quantity let me write it again. Yeah, so this quantity is 0 comma b cross 0 infinity mod e minus xy sin x d m1 cross m1, right? So now you note that this, since we are taking the modulus by a part, I mean the first part, you can write this as iterated integral. So let's write it as 0 to b 0 to infinity e minus xy sin of x and then dm1x dm1y, sorry, and then dm1x. Okay, so now now what you can do, you can, this dmy will be the in Riemann integration, so dy dx. Okay, so now you can write it here. This is nothing but, so 0 to b you just take out. Okay, and then okay, so you have mod here, so mod sin of x, and this integration you can write e minus xy upon minus x. So when you integrate with respect to y, and the limit would be 0 infinity, and then this would be dx. Now you do 0 to b mod of sin x. Okay, and then here if you put infinity you will get 0, and then you will get 1 by x, right, dx. So this is 0 to b mod sin x by x, right? So now you know that this is a bounded function, right? So this is a bounded function. In fact, this is less than equal to 1. So this is 0 1, this is, sorry, 0 b, this is 1, and then dx. And this is b, so which is finite, right? So we can use Fubini, right? So this is by Fubini, the c part, remember, and this is the reason. Okay. Okay, so we can apply Fubini here. So we have interchanged it. Now again we'll solve it. I mean it's the same thing. Okay, so nothing special here. So you integrate with respect to x. Just a second. Yeah, okay, so here we'll integrate first with respect to x. Okay, because if you do with respect to y, then there will be a problem. So here if you start, so at this point, why we wanted to change this integration, because if you integrate with respect to y, there will be some problem, right? So I don't know, just a second. So if I integrate first with respect to y, what will be the problem? Okay, yeah, so if you integrate with respect to y, so what you get is e minus xy by minus x, 0 to infinity, and then sin x, right? This is what you get. And then when you substitute, you will get 1 by x sin x integration 0 to b dx, right? The point is how to evaluate this integral. Okay, so it will be more difficult to find this integral. Okay, so that's why what we do, we change this order of integration, we change. Okay, so now let us see what this will be. Okay, so our goal, so let me mark this 1. Okay, so we have to evaluate this integral. Okay. So let us first see this integral. Okay, this one. Let us first try to see this integral. So here b is there, so you can consider this as a function of b. Okay, so I mean for fixed b I am considering, and if you integrate this, Okay, so you'll get something in terms of y possibly. So let's take, I'm writing this as IBY. Okay, so for given b, and this as I mean for fixed y, I mean, or y will change ultimately, because you know this y is varying from 0 to infinity. Okay, so that's why I'm writing IBY as this integral. Now if you do integration by parts, okay, so let's do that. So what you do, you take this e minus xy outside, and the integration of sign would be cos x, so 0b minus, uh, you do e minus xy, and then you have minus y, and then cos of x dx 0 to b, right? Yeah, so this will be there. So and now if you put here instead of x b, so you will get e minus by cos of b, and if you put 0 you will get minus 1 1, right? So and then you have this quantity. So now again use integration by parts. So let me first take y outside, then you have 0b e minus xy cos of x dx, right? So this is what we have. So again let's write e minus by cos b, just a second, the sign of integration, so this will be minus, plus minus, right? Here also it will be plus, here it will be minus, right? Otherwise if I integrate it again, then there will be problem, right? Okay, so I mean the integration of sign is minus cos. Okay, so this is there, minus cos b plus 1, right? Okay, so now you can rewrite this as, let me write 1 minus e minus by cos of b, and this minus, again use the integration by parts. Okay, so if you use it, just a second, oh, why I have put plus here, it should be minus, right? No, it's plus, it's fine. So just a second, so you do e minus xy, you put minus sign, and then you have minus y, and then you have minus cos x, right? So yeah, so this will be minus, yeah, it's fine. Okay, okay, now let's do integration by parts once again. So what you have is e minus xy. Now integration of cos x would be sin x, the limit would be 0 to b in this, and then you put minus sign, you will have 0 to b e minus xy, and then you have minus y, and the integration of cos would be sine, right? Now this would be 1 minus e minus by cos of b minus y. Now again you substitute, so at b it will be e minus by sine of b. At 0 it will be 0, so it's minus this, and now you have here, so this will be plus, this will be plus, and then so this minus minus plus, and then this minus will be minus y square 0 to b e minus xy sine of x dx, right? So this is again IB of y, right? So it's the same quantity. So ultimately what you get is IB of y will be 1 minus e minus by. So you take constant common here, and then you have cos b minus y sine b, and in the denominator you will have 1 plus y square, right? So this will be the value of this IBY. Okay, so which was this integral basically, right? So this integral. Okay, so now you have evaluated this integral. Now you have to integrate with respect to y, right? So that was your main goal, right? So this integration, or if you want you can, okay, let's see. So therefore integration 0 to infinity 0 to b, what was that, e minus xy sine y sine of x dx dy. So you have to integrate this whole quantity with respect to y. Okay, and so let me write in this fashion so that it is understandable. So we started off with this 0 to b sine 1 by x sine of x, right? So this was our initial term. We used some integration for this one 1 by x, and then we got this quantity, right? So this is equal to this. Now you have to integrate this with respect to y. So let's see. So 0 to infinity, so this quantity is 1, so let's write 1 plus 1 by square minus e minus by, and then you have cos b minus y sin b by 1 plus y square, right? So this whole integration with respect to y. Okay, now the first integrand is nothing but tan inverse y. So you integrate from, so this is the value 0 infinity minus 0 infinity e minus by cos b minus y sin b by 1 plus y square, right? Yeah, so dy, right? Yeah. Maybe okay, I hope everything is correct. Okay, so whatever.
Sir,
Yeah.
in bracket there should be plus. We are taking e to the power minus by common. So it will be
Oh,
plus.
exactly. Here it should be plus. Is there some other error also? Let me know if there is something else. Okay. Yeah, I think. Okay. I hope there is no other error. I don't know. Okay, so here it will be plus. Here it will be plus. Okay, and then what else will be there? Okay, so you have this thing. Now you know this tan inverse y, if I put infinity I'll get pi by 2, and tan inverse 0 will be 0, so it's gone. So you have minus 0 to infinity e minus by. Okay, and then what else, this cos b plus y sin b 1 plus y square dy, right? Yeah. Okay, I hope, I don't know. Okay, now you know that this is pi by 2, so now you have to take limit b going to infinity, right? So I mean you had to find the value of this quantity when b goes to infinity, right? That was your main problem, right? So now when you put b equal to infinity, where does this go? That's all you have to check, right? Yeah, I mean, is this clear so far? Tell me.
Yes, sir.
Okay, so now you have to make sure what will be this integral. Okay, so let us try to see this integral. Okay, okay, so now so my claim would be that the limit of this quantity limit b going to infinity is 0, right? If I can prove this, then I'm done. So let's see. So if you see this quantity, okay, let us do a change of variable. So I'm naming this by as new, let's say z equal to by. Okay, so if you do this type of change of variable, what is there is 0 to infinity, you will have here e minus z. Okay, cos of b would be, what will be cos of, who is this so cos of b will be as it is. Now instead of y I'll have z by b, and here I'll have sin b. Here I'll have 1 plus y square will be z square by b square, and then dz would be dy would be dz by b, right? Now if I do it further, 0 to infinity, so limit will not change, so e minus z. Here take b LCM, so you'll have b cos b plus z sin b, okay, and then you will have, so b square plus z square by b square, so here 1 by b is there, and here b square is there, and here you have 1 by b again, right? So dz, so all these will cancel out. 1 by b would be b square, and this b square, this will cancel, so this will be gone, right? So you'll have here 0 to infinity e minus z b cos of b plus z sin of b b square plus z square dz, right? So now you have to make sure that this goes to 0. One thing you can clearly see, that as b goes to infinity, the above, so this is bounded, right? This is less than equal to 1, this is less than equal to 1, this z is anyway, I mean, this is something, but as a function, let's see. So if z is fixed, you can see that this, in the denominator, in the numerator you have b, in the denominator you have b square. So as b goes to infinity, you can prove that this goes to 0 as b goes to infinity. Okay, now you have to use dct to show that this whole integral will converge to 0. So that I'll leave as an exercise. Domain you see here is 0 infinity, right? So if you get any constant function m, okay, suppose you get that this function f, or I mean this whole function, let's say this g, so if you prove mod g is less than equal to m, then this is not enough, because this m is not in L1 0 infinity, so this is not in L1 0 infinity, so you cannot use dct. So you have to find some other function g tilde of x which is in L1, okay, so which is integrable. So you try to look for that. Okay, do you have any other question? Okay, then I'll just stop the meeting here.